Hello guys, today we're going to see what happens when we rotate a circle around its origin. But before getting into the maths, let's first visualize what happens. At first glance, if we rotate a circle around its origin, what do we get? Well, apparently we get the same circle. And what do I mean by the same circle? Well, we know that the equation of a circumference centered at the origin, it's x squared plus y squared equals the radius of the circumference squared. Now, why we chose this circumference to be centered at the origin? Well, because it's a bit simpler, the equation, because we don't need to incorporate the coordinates of the origin. But this applies to every circle in the xy plane. And what do I mean that it is going to be the same circle? Well, I mean that it is described by the same equation. So if we rotate this circle, we are going to end up with the same equation we started with. Basically, two objects are equal to each other mathematically if they describe by the same equations. First of all, notice that every point of this circumference is described by x and y, those two coordinates. And we can imagine every point of the circumference as a vector pointing in that particular point. So a vector that has coordinates x and y that obviously obeys this equation. Now, how can we rotate this circle? Well, we could apply a linear transformation that applied to this vector x, y gives us another vector, for example x, r, y, r, after the rotation. So what is going to be this linear transformation? Well, a linear transformation is given by a matrix, so the matrix we are going to use is the rotation matrix. So cosine theta minus sine theta, cosine theta. And if we apply this rotation matrix to our vector with coordinates x, y, and by this vector I mean every vector that describes every point of this circumference, we get our new coordinates xr and yr. This is our linear transformation. If you don't know what I'm talking about, well, I made a video about the rotation matrix, deriving it and explaining how it works. But you can even rotate this circle without going through linear algebra and rotation matrices, linear transformation, etc. But we're going to do it this way. Okay, now in order to get the components of the rotated vector, we just have to compute this matrix vector multiplication. So this is going to be x cosine theta minus y sine theta, x sine theta plus y cosine theta. And this is our new vector, the vector xy rotated. And in particular, this is going to be the x coordinate, and this is going to be the y coordinate. Now that we have the x coordinates and y coordinates rotated by some angle theta, we just have to substitute those two coordinates in our circle equation because every point of the circumference obeys this equation. So let's do it. So we have x cosine theta minus y sine theta all squared plus x sine theta plus y cosine theta all squared equals the radius squared. And now we just have to work out this equation. So we have x squared cosine squared theta plus y squared sine squared theta minus 2xy cosine theta sine theta plus x squared sine squared theta plus y squared cosine squared theta plus 2xy sine theta cosine theta equals r squared. Now, as you can see, we have this term and this term right here equal to each other but with opposite signs, so we can cancel them out. And now we can reorder a little bit this equation, and you might notice something very interesting. We have x squared cosine squared theta plus x squared sine squared theta plus y squared sine squared theta plus y squared cosine squared theta equals r squared. As you can see now, we have an x squared here, and y squared and y squared. So we can factor them out. So we have x squared that multiplies cosine squared theta plus sine squared theta plus y squared that multiplies sine squared theta plus cosine squared theta, and this equals to r squared. As you can see, we have approximately the same equation we started with. We just have this term here, cosine squared theta plus sine squared theta, and sine squared theta plus cosine squared theta. But you may recognize from trigonometry that this is a very famous identity, and this equals 1. And why does it equal 1? Well, if we imagine this circle that is not, but let's imagine it has radius 1, so it is the unit circle, then the sine is going to be this side right here, sine of theta, and the cosine is going to be this side right here. So from the Pythagoras theorem, we know that the square of cosine of theta plus sine squared of theta is going to be equal to 1. So we end up with x squared plus y squared equals r squared. And as you can see, this equation is the same we have started with. So if we rotate a circle around this origin, nothing happens. It is described by the same equations, and therefore it is the same circle. Now you may say this is a very simple solution and a very simple thing to do. Why we had to do all of this? Well, sometimes we think that maths is too abstract, but when you can do mathematically some things that you can easily visualize, like this one, it was reasonable that it is going to be the same circle after rotating it, since if you rotate a circle around its origin, nothing happens. And maths told us that this is the way it is. We started with this equation and we ended up with the same equation. But this is a nice result because it shows that maths works, is something useful, is something real. If you enjoyed my video, leave a thumbs up, share it with your friends, don't forget to subscribe to my channel and leave a comment below. Let me know in the comments if you would like to see a video about the rotation of a circle around a certain point in space and not just around its origin, or a rotation of a circle in 3 dimensions. That is something incredible and very cool to do. So let me know it in the comments. Until next time, bye.